I'll begin with a word of prayer. Dear Heavenly Father, we thank you for this day. I thank you for the break. Pray that you help us to use this time wisely just to prepare for the test this Wednesday, Lord. In your name I pray. Amen. All right, let me try one more time. Let me try the, maybe it's the internet here. If I try the wired internet. So usually after I scan it upstairs, it shows up here pretty much immediately. I split it into two pieces to make it smaller. You may have noticed the homework is somewhat long. Oh, look, something showed up. Woohoo! Well, there's the, that's funny. The second thing I scanned showed up first. Well, I now have this. Oh, wait, no, what's this? So by the way, if you're emailing me at this point, and you're emailing me, if some of you guys have your Outlook like going through Gmail or something, I believe. So anybody who does that and sends me an email through that rerouted through Gmail thing, when I respond to it from my Outlook, it bounces back. Gmail thinks I'm spam. I mean, I think I'm spam too. But anyway, long story short, if you want to communicate with me outside of Outlook, if you've got one of those setups, don't waste your time emailing my Outlook because I can't respond to it. So you should contact me by my other email, which I'll tell you if you ask me. So I don't want to say it right now. Okay, so anyway, you guys have any questions? It's really annoying. It's gotten to the point where all of my Outlook, if I send an email from Outlook to anything external to Liberty, it bounces back. So I have not had a chance to consult with the powers that be to try to fix this problem. I figure the simple solution is just not to use Outlook and just always use Gmail. So, all right. Come on. Oh, so turn your homework. Yeah. Before I forget. Thank you. Thank you. Hey, everybody's? All right, so, of course, excluding the two of you I've talked to individually, but let's see here. I've got, let's see, Audrey, no, Benjamin, oh, Audrey, Benjamin V? No. Emily, oh, wrong class, never mind. Yeah. All right. Got that out of my system. All right, so attendance. Let us not forget to take attendance. So we'll add yet another column to this thing. What is today's date? Wait a minute. You can add another column, 26 apparently. Okay, guys, so is there a particular question here you want to talk about in mission 6? No? All right. Yeah. Just literally anything? Let's start at the beginning then. Let me kill part of the lights. All right, before I get too immersed in this, let me just say, what's test 2 about? It's about the material that we've covered since test 1, obviously, right? So what is that? Definition of a vector space. What's a subspace, right? What's a linear transformation? Kernel, range. How to find basis for the standard subspaces attached to a matrix. What are the standard subspaces attached to a matrix? The null space and the column space, right? And on a rare occasion, I'll talk about row space, right? But we've seen that the column space and the null space are the more important ones because of their connection with the kernel and the range of a linear transformation. We've looked at intersections of subspaces. We've looked at the sum of subspaces, how to find the matrix of a linear transformation, how to find the coordinates of a vector with respect to a basis, how to make a basis, right? Given a partial basis, how do you complete it to a basis, right? Start with a basis for a subspace. How do you find a basis for the whole space, right? This is something we've talked about. And then finally, what's a dual space? What's a quotient space? I think how do you judge equality of cosets? These are all things we've talked about. Right? Okay, so that's just a kind of a litany of things that are likely to come up. For subspace, well, for the definition of vector space, the simplest thing to do is just to give you a list of things and say, is this a subspace or is this a vector space or not with respect to a given field, right? And how you judge whether it is or not, basically, usually, more often than not, comes down to arguing that one of the axiom fails, right? If it's a no, maybe 0 is not in there, maybe it's not closed under addition, maybe it's not closed under scalar multiplication, something like that, right? Yeah.
I remember you talked about the axioms. Do you want us to memorize those, or will you give us that list?
I want you to memorize the content, but not the numbering. Yeah. You should know the axioms. You don't have to be able to enumerate them as in, if I have a question which involves the kind of picky axiom by axiom calculation, I will reproduce the definition as it appears in the notes in its totality, and then ask the question following up. Like I showed you guys in the help session, was it? I actually projected an old test too and showed how that went. Or maybe it was test, I forget which test it was, but yeah. Question? Oh, okay. So this one, in problem, what was it, 64? I think problem 64, we had to find the intersection of two subspaces, right? So this is really just a play on that problem in some regard. So the way I attacked it this time was just to look directly at what the condition meant if I have a vectors in both of these. And that means that f of x is, on the one hand, a times the first vector plus b times the second vector. On the other hand, there has to also be c and d such that c times this vector plus d times that. There has to be some a, b, c, d such that these are equal for it to be in the intersection, right? Because if it's in the intersection, it's in both, right? And so then I equate these. I equate coefficients. Remember, we proved linear independence of the monomial basis, 1x, x squared, x cubed. So I get b equals c, a equals c, a equals d, b equals d, which when you put it together gives me a equals b equals c equals d. So what's in the intersection is just scalar multiples of the polynomial 1 plus x squared plus x cubed. This is what's in the intersection, because that's an arbitrary thing in the intersection. I just showed it has that form. So what's the basis for the intersection? Well, it's just that vector in a set, right? So that's 91. Now, the alternative way that I did in problem 64 was I found equations to characterize the subspaces, right? So from an equations perspective, W1 is all polynomials like that, such that b is equal to d and a is equal to c. W2, it's all polynomials like this, such that a is equal to b and c is equal to d if you look at it. So when you put these two sets of equations together, you just get a equals b equals c equals d, which gives us the same thing again. That's the other way you could look at this problem. Either directly as a set theory / intersection, or just combining equations. Anyway, that's what it is. for W1 plus W2, W1 plus W2 is by definition the set of all, you know, you take something from W1, take something from W2, add it together. The set of all those things, well, that's W1 plus W2. So if I take f of x in here, that means that there exists f1 and f2 in W1 and W2 respectively. And by the way, that means that I can write f1 as a sum of these guys, these guys, and I can write f2 as a linear combination of those guys. So in summary, f of x is a sum of these guys. But what's that mean? Well, that means that beta 1 union beta 2 is a basis for W1 plus W2, right? Now, I don't think, you know, if there's a problem like this on the test, I wouldn't expect you to actually go through all this calculation. I'm trying to convince you here in this problem that if we have a sum of two subspaces, to find the basis for the sum, we just take the union of the bases. But that doesn't quite work, because when you union the two bases, it doesn't have to be linearly independent, right? In fact, these are not linearly independent. There's a linear dependence amongst these vectors. How do I discover what that is? Well, it's a little bit complicated, actually. So I chose to use a coordinate approach. What I did was I looked at the matrix of coordinate vectors for the beta 1 union beta 2 basis, which gives me this. I do my row reduction. I get to that. That shows me that, in fact, the first three vectors, this, and this, can be taken to be linearly independent. And the fourth vector, 1 plus x cubed, can be built from 1 times the first one plus the second one minus the third one, right? That's the column correspondence property on the matrix, which I then filter back through the coordinate map to get the linear dependence back in the abstract vector space. So anyway, there's my basis for W1 plus W2. It's this, this, and this. As you can see, the dimension's 3, which is in good agreement with that theorem that I asked you to check, namely that the dimension of the sum is the sum of the dimensions of the subspaces minus the dimension of the intersection, which in the previous problem you've calculated as 1 dimension because it's just the span of that one vector. So of course 2 plus 2 minus 1 is 3. Okay. Any questions? Okay, well, fine. 93. What was the question? What was this about? I forgot what the question was. Now, I actually ignored my instructions in some regard. I didn't actually follow through with following the notes because I thought it might be more useful to do it in such a way that you'd actually have a chance of doing it if I was to ask a similar question on the test. Right? If you do it the way I did it in the notes, like doing it that way in the test is kind of out of, I mean, it wouldn't be wise because you'd have to adjoin this big matrix of ones and zeros, right? And do row reductions on huge matrices, blah, 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 blah. It's complicated. But there's a simpler way of thinking about this. So I took the standard matrix of T. I row reduced the thing to that. All right? These are the row reductions that get to that. And so from that, I can calculate the basis for the null space, right? I can calculate a basis for the null space of the standard matrix of T, which, by the way, is a basis for the kernel of T. So anyway, the usual calculation, x1 is 2x3, x2 is minus 2x4. Put that into the generic x in the null space. It gives me these two vectors as a basis for the null space. So this is a basis for the null space, right? And then, then I want to extend the basis for a null space, the basis for the null space to a basis for all of R4. All right? And I did this rather complicated calculation down here to figure out what I could do. It turns out that I think I can pretty much pick what, looking at this, what can I do? If I want to have, take this base, take these two vectors and add, take the union of two additional vectors from the standard basis, what choices will actually give me a basis for R4? Looking at this calculation. Which, if I take, these four vectors, which of these four vectors adjoined with these two give me a linearly independent set of four vectors? Can you tell me? I mean, certainly if I take the first four, we're good to go, right? We can take basically this one, E1 and E2. That gives us a basis because looking at these four, we have linear independence, right, by column correspondence property. Could I also use, what about, looks like I could also, there's no way to get this column from these two, right? And there's no way to get this column from these two either. So it appears to me you can't go wrong. In fact, this is very forgiving. As long as you take the two things in the kernel and you pick any two of these, I believe it gives you a basis. Am I wrong? I don't think I'm wrong. But. Now, so the idea here, guys, is that I eventually will find my markers. Give me a second here. So we have T, a mapping from V to W. I'm trying to show you how to build a basis. I'm trying to explain to you guys how we can build a basis, beta, gamma, such that it looks like the identity matrix, a k by k identity matrix with zeros. Right, so what basis beta here do I use? What basis gamma here do I do to make that happen? So what I'm trying to say is what I can do is I can say, okay, well, what I need to do basically is put something in here, union with basis for the kernel of T. See, if I put the kernel for T at the end of the basis, that automatically makes these zeros here, right? And then I just need to figure out what to put over here. I need things that don't map to 0. Not sent to 0 under T. So that was actually the point of this calculation, was to find those vectors. But there's an easier thing you could do, right? Like, you don't really need this calculation to figure out how to extend beta naught. Think about this. If I just put E1 times T, what do I get? I mean, T times E1, matrix of T times E1, I get 1, 1, 2. If I do the matrix of T times E2, I get 0, 3, 0. Those are non-zero. Therefore, E1 and E2 are not in the kernel. So I could just do E1, E2, and then the basis for the kernel, my beta naught, and that would give me a basis for R4, which would have this desired pattern. Then the question is, how do you choose gamma? Well, you choose gamma. So for R1, let's say this is F1 and F2. I said E1 and E2, right? So gamma, I just make T of E1, T of E2, and in this specific context, it's three-dimensional, right? So I just need to figure out something to put over here. So T of E1 and T of E2, I just told you what those are. There's 1, 1, 2. And this one is 0, 3, 0. So you just got to fill in the blank, put anything there. Anything you put there, this will make the matrix of T look like a 2 by 2 identity matrix with zeros everywhere else. Is that right? Yeah, so specifically it's going to look like for this problem. So remember that the matrix of T with respect to beta gamma is what? It is T of the first thing in beta basis, so T of E1, the gamma coordinate, right? T of E2, the gamma coordinate of that, and then T of, I don't have names for these stupid things, but 2, 1, 2, 2, 0, 1, 0. T of, what's the other one? 0 minus 2, 0, 1, 0. Emma, could you hit the lights for me for a second? Sorry. Oh, thanks for helping her. Sorry about that. So my point was, this is, by definition, this is the matrix of T beta gamma, right? We feed the matrix, the basis in the domain, which in this case, by construction, E1, E2, then the two things in the kernel, right? So putting the things in the kernel at the end of the basis makes these 0, right? And this is just equal to 1, 0, 0, and 0, 1, 0, provided what? Provided that I force that to happen. I just make those the first thing in the gamma basis and the second thing in the gamma basis to put that 1, 1, 1, 0, 0, and 0, 1, 0 there. So the only thing that's left, really, is to pick something to put over here. What do you guys suggest we put here to finish out the gamma basis? The choice is not unique. I cannot, anything except a linear combination of these two works, right? How would you figure out what arbitrary vector could be put here? Like if I say that the arbitrary vector we're looking for is ABC, can you tell me what condition on ABC is needed for this to be a basis for R3? What does that mean, basis for R3? It means linearly independent spanning set, right? You guys are still on break, huh? Okay, so the matrix of gamma would be 1, 1, 2, 0, 3, 0, and ABC. So how do I decide whether or not that matrix is made of linearly independent columns? Calculate the determinant, right? If the determinant's non-zero, then the columns are linearly independent. So that'll give you a specific equation for ABC. I mean, so here's what I would do. I would just say, okay, so A equals 0, B equals 0, C equals 1 works, right? Because then this has the determinant of the matrix gamma would just be 3C in this case, right? Which is 3, which is not equal to 0. So in other words, fill in the blank. Nice choice here is just E3. Is that choice unique? Certainly not, right? Is that what I did when I wrote the solution here? Oh, it is. So, huh. Oh, okay, so yes. Yeah. This is not the unique solution. I just happened to find the same choice of basis, by the way. All right, I'm going to move on. I've spent entirely too long talking about this problem. Here's a pretty standard gift test question. Find the coordinate vector for V being 7, 9 with respect to the basis beta being 2, 2, minus 1, 1. We have derived that the coordinate vector with respect to a basis, and this is just for Rn, right? For an abstract vector space, you actually have to do more calculation. You can't just put stuff in a matrix and invert it, right? Remember, this is for column vectors. But anyway, since it is, and since it's 2 by 2, I have a formula for the inverse, right? And so I get 4, 1 is the coordinate vector. And then it's easy to check, right? So if this is right, then 4 times the first thing in the basis plus 1 times the second thing in the basis ought to give me back what we started with, 7, 9, and in fact it does. So, all right. Problem 95. What was this problem? Here I give you 2 bases, beta and beta bar, and I wanted you to find the change of coordinate matrix going from the beta to the beta bar coordinate system. In other words, the matrix such that when I take the beta coordinate vector and I multiply it by this matrix, I get the beta bar coordinate vector. It's the change of basis matrix. And I can also look at it as the matrix of the linear transformation going from here to here, which would actually be this thing right here. It's really the matrix of, what is that map going from here to here? This is phi beta bar. I forgot to label it. So going from here to here, I think we would have phi beta bar composed with phi beta inverse, right? So you could say that this, but anyway, let me just look at it more directly. So what's the coordinates of this vector with respect to the beta basis? Well, it's just ABC, right? With respect to the beta bar basis, I have to re-expand this centered at 2. We learned how to do that in calculus too. Taylor's theorem tells us how to do that. It says it's f of 2 plus f prime of 2 times x minus 2 plus f prime prime of 2 over 2 times x minus 2 squared. And so actually fleshing that out for this specific ax squared plus bx plus c gives me 4a plus 2b plus c for f of 2. It gives me 4a plus b for f prime of 2. And it gives me a, because f prime prime is give me 2a, but Taylor's theorem says divide by 2, so 2a divided by 2 is just a. So that's why I got this a here, all right? And so the change of basis matrix would go from that to that, and as you can see, that should be 4, 2, 1, 4, 1, 0, 0, 1, 0, 1. There are other ways of calculating that, but that's one. Here's the other way. If you want to calculate the change of basis matrix, a nice thing to remember is that it is the matrix made of the coordinate vectors of the initial basis with respect to the basis that you're changing to. So the beta basis is x squared x1. I'm finding the coordinate vectors of this, that, and that with respect to the beta bar basis. So, and to see why this is the case, it comes from this calculation down here, which is that this is equal to, in fact, that. How did I know that this is equal to that? Where's this mysterious equality coming from? That is Taylor's theorem, right? Or if you're just good at algebra, you're like, this is obviously equal to that. That's actually not entirely crazy if you start with the a, because you have to have a times x minus 2 squared in order to match ax squared, right? The only way to get x squared from this, that, and that is from the x minus 2 squared. That forces you to put an a here. Once you're forced to put an a here, that forces you to do other things as you kind of work backwards. I can actually do that without Taylor's theorem, but Taylor's theorem is just way faster. That's why I'm telling you that way. Anyway, there's the coordinate map. Phi beta bar on this is equal to that. So, all right, enough about this, enough about this. But my larger point here to you guys is there's two things that make this problem worse than the previous one. One, it's three-dimensional, right? Three-dimensional calculations, I was a little bit pickier. But the other is that this is on polynomials, right? So the technique I used in the previous problem won't work here. I can't just shove the polynomials in a matrix and calculate the inverse of that matrix, right? I have to sort through the ideas in a different way. Yep.
For Taylor's theorem, do we have to, like, would there be a case where you have to do that to f triple prime or something like that?
Sure, it could happen. You're supposed to know Taylor's theorem.
Okay.
It's arbitrary order.
And then dividing by 2, where it was the f double prime over 2, is that because it's f double prime or because it was x minus 2? So if it was x minus 1, would you still be divided by 2 there?
Yeah. So the Taylor's theorem, it's generally speaking, f of x is the sum k equals 0 to infinity of the kth derivative at a over k factorial times x minus a to the power k. So yeah, the division is it's the division by k factorial. It's not this k has nothing to do with that a. That's just circumstantial. Yeah, yeah. Indeedly. Indeedly. Now this one here, problem 96, was a coordinate change question on 2x2 matrices, and I usually call this the lexicographic basis, like that's the usual. If you wanted to, in some sense, this is the sort of standard basis, but I wouldn't say that because I reserve the term standard basis for Rn, whatever. And then I gave you this weird. Here's the diagonal one, the 1, 1, the 2, 2, and then these guys. The symmetric one and the anti-symmetric one, right? And so I gave these names, F3 and F4, and I would point out that E21 is F3 minus F4 over 2, and E12 is F3 plus F4 over 2. Recognizing those two things makes everything else really fall into place. Of course, you could set up 4x4 systems of equations and discover much the same, but in any event, the change of basis matrix going from that to that. So first of all, E11 is the first thing in both, so that just gives me that. E12 is actually, like I said, it's 1/2 of, where is it? 1/2 of F3 plus F4. That's why I put the half down here. E21, well, that's F3 minus F4 over 2. That's why I have a half minus half here. And finally, E22 is, let's see here, this is, why did I do E22 last? Oh, because it's last in beta, duh. So E22 is the second thing here, which is why I put an E2 there. So, great. Then here's find the matrix for the transposition map. So I need to, and I think I asked you to calculate the matrix with respect to what? Beta bar, was that right? I've not written it here, but in the instructions it says calculate L beta beta bar. So I have to go through and figure out what's the beta bar coordinates of L of A. And so what I did was I just rewrote well, A is A, B, C, D, so A transpose is this. I need to figure out the beta bar coordinates of that. So I have to express this in terms of the beta bar coordinate vectors, basis rather, which is E11, E22. And so what I do here, this is E1, this is C times E12, but E12 is F3 and F4 divided by 2, summed. And E21, well, that's F3 minus F4 divided by 2, so I put that in here. And then I just rewrite this. So I've got A copies of E1, D copies of E2, 2, and B plus C copies over 2 of F3, C minus B copies of F4, so that's why this is the coordinate vector. And then the matrix is whatever I need multiplied by A, B, C, D to get to that, which is down here. Any questions? Oh, man. I'm going to go on here. Problem 97. So I gave you that V1, V2, and V3 are this. I think I actually meant to put V2 here, but I accidentally didn't. It doesn't make the problem wrong, it just makes it less interesting. So I stuck with it and didn't correct it. Did some of you put a 2 here just to?
I think I accidentally did.
I hope the grader won't take off points. I mean, I think if you put a 2 there, but you still still work it out, it should be fine. I don't really think we should. If he takes off points for it, you come see me. I'll give you the points back. Okay, I mean, it's fine. Anyway, with this choice of V1, V2, V3, we can relate the standard matrix to the T beta beta matrix by this coordinate change formula, right? So I can solve that for the standard matrix, which I don't know, to get this. And by the way, this T beta beta matrix is this by the given data, because I've got V1, 2V1, 3V3, which gives me this, this, and this for coordinate vectors. And then I just have to multiply by those. I wonder, though, did you do it the right way? Did you think about this multiplication the right way? You should notice that this is actually a block diagonal matrix, so you can calculate the inverse directly. Yeah? Don't need to do a big, long calculation here, because this is a 2 by 2 blocked with a 1 by 1, so the inverse is just the blocks of the inverse. Well, the inverse of the blocks, I don't know, words. But so it's that, which is, by the way, 2 by 2 matrix inverse formula of this, so I get that. We'll move on here. Our time is limited. I'd still like to talk about previous missions. So let's see here. I really don't want to talk about this one at the moment. It's essentially the same as the one I spent a bunch of time talking about earlier. The thought process, really. Problem 99, I'll let you look at the solution of it. It's a little bit subtle. Is this the one I'm thinking of? Oh no, this one's not subtle. This one's fine. I'm thinking of the other one. So again, the problem is centered around understanding what does T beta gamma mean. It's the matrix of T with respect to the beta gamma basis, right? So it actually tells us what these are, coordinate vectors. We learned that the coordinate vector of 1 is 1, 0. The coordinate vector of x is 0, 1. That x squared and x cubed are in the kernel of T, right? That's all given to us by this matrix. So I can see that, and if I work it out, this right here, let's see here. So for example, because T of 1 is 1, 0, that tells me that T of 1 is this matrix, right? Because that's the first matrix in the gamma basis, right? And because T of x is 0, 1, that tells me that x maps to the second thing in the gamma basis, which in this case is 1, 0, 0, 1. So I get this, I get that. X squared and x cubed are in the kernel. Those don't go anywhere. And the A gets sent to 0A, A0, and then the B gets sent to B0, 0B. When you add them together, you get this formula. So I think this is a decent, it's a good, healthy question. Hopefully nobody got stuck on that one. I'll let you look at the rest of it there. I'm going to move on. Come on. Well, actually, I won't move on because, well, there, now move on. This one was trickier, right? I think part A, a lot of you should have got without too much flinching, because I give you a pretty significant hint about how to calculate the kernel. Even if I hadn't given you that, I think you probably would have still figured it out. But I can find the kernel from the null space because the kernel, the null space in the coordinates is related to the kernel in the actual domain. They're transported, the kernel transports to the null space under the beta coordinate map. In the same way, the range transports to the column space under the gamma coordinate map. And so if I have either the range or the column space, if I have either the kernel or the null space, and I know what the coordinate systems are, I can get one from the other, right? I mean, it's a complete correspondence under the coordinate map. So anyway, here I can take the inverse image under phi beta inverse of the null space. The null space is this span. By the way, we can actually move the map inside the span like that. That makes sense. That's using theorems that we've developed. And then this is exactly 1 plus x, and that's exactly x plus 2x squared. And there you go. That's the kernel. And likewise, for the range, I can use the gamma coordinate, the inverse of the gamma coordinate map to lift the column space back to the range. And it's pretty much the same way. So I get the range as this. Part B was probably the trickiest part in this whole problem in your whole homework. I mean, we know that the range is one-dimensional. It's got to be a multiple of the vector e to the t plus cosine t, right? So on the one hand, t of this stuff has to be some number times e to the t plus cosine t. But on the other hand, now, first of all, I tried to do this. At that point, I realized, oh, I didn't give you guys the matrix, did I? So this approach got stuck dead in the water right here when I realized, oh, you idiot. You're thinking of the previous problem where I actually gave you the matrix, right? I didn't give you the matrix. I just told you the null space and the column space, right? So it wasn't, I don't have this. And by the way, the null space and the column space do not uniquely fix the matrix, do they? If you have a matrix A, and you take that matrix times 7, they have the same kernel, they have the same null space, and they have the same column space. Multiplying a matrix by a number does not change the null space or the column space. So certainly giving you null space and column space does not uniquely fix the matrix there. But on the other hand, we know that 1 plus x is in the kernel, and we know that x plus x squared is in the kernel, x plus 2x squared in the kernel, which tells me that t of x is minus t of 1, and t of x squared is 1/2 t of 1. So it all goes back to t of 1. So I use linearity, and I'm able to write it as a minus b plus c over 2 times t of 1. But because the range of t is this, that means that t of 1 has to be a multiple of that. And so it gives me this formula. Again, like I said, it's not unique. There's a parameter alpha. And that's what the matrix looks like. Not that I asked for it, but there it is. So I know some of you found the matrix directly, and that's also fine. It's just my way of thinking was not to look at the matrix, but to look at the vector spaces. You know, it's same song and dance. Problem 101. Look, again, I'm really not looking for much here. The point was, for part A, saying that v sub I is defined by the values on the basis linearly extended, that makes sense, because if we calculate vi of x, we get ci, right? And this is a unique thing. You know, the ith coordinate for a vector, is that a single valued thing? We've discussed that the whole point of having linear independence and spanning for a basis is that for a given vector in the vector space, it uniquely fixes a set of coordinates, right? So in particular, the ith coordinate is fixed, right? So this defines a function, and by assumption, it's linear. So yeah, the v upper I defines a dual vector. I don't know. I could understand how you could go nuts with problem A, because it doesn't seem like I'm asking anything I haven't said already. All right. I want you to come. Basically, I was trying to get you to come to terms for it for yourself. And part B and C, you almost will end up solving in part A. depending on how you look at it, Phi beta of x is well, x is this, right? And something I haven't emphasized as much as I like to most semesters is that the coordinate map, what is it? It is a machine that does what? It changes the abstract basis VI to the standard basis EI. That's what the coordinate basis, the coordinate map does, is it changes your abstract basis to the standard basis. And to find the inverse of the coordinate map, you just do the opposite. You send E1 to V1. You send E2 to V2. That's how to find the inverse to the coordinate map if you have the basis sitting there. All right. Problem 102 was actually not that bad. I'll let you look at it, okay? I mean, part A is worth me talking about for a second. I have said so little today about subspace test, but what is it so likely to your test is going to be about? In fact, it is a shame that I've spent so much time today on mission 6, because we also had what? 5 and 4, and the test is probably more about those, right? In all likelihood. Because there's lots of simple questions that are basic theory questions there that make good test questions, right? Is this a subspace? Stuff like that. By the way, I should always remind you guys, what are the 2 ways to check something's a subspace? Number 1, this way, right? Identify it as a subset of a given vector space, in this case, dual space. Check the subspace test, right? Non-empty, closed under scalar multiplication and addition. I do them both at once by checking C alpha plus beta, right? What's the other way, though, that you guys sometimes forget about? If it's a span, right? So if you don't notice something's a span and then you try to do the subspace test, it makes the question take about 5 times as long as I intend. So look for spans if you can find them. Because once you identify something's a span, you say, this is a span, therefore it is a subspace. Oh man, this stupid scanner has robbed us of our time. I wanted to write down some isomorphisms for you guys. Here's one at least. I didn't ask you to find this, but here's the isomorphism in that last problem. If I take a cubic polynomial and a 2 by 2 complex matrix, I want to get a pair of symmetric matrices. What do? You just list out the parameters one at a time. So I got my A, my B, my C, then D, and then E, and then H. You notice, actually, these follow automatically because it's symmetric. So you just write down the upper diagonal and this kind of thing. B, C, and E come from automatically. Then I got to H. Then I went over here J, then K, then L, then M, then P, then Q, and then the K, the P, and the L follow automatically. And there you go. That's the isomorphism explicitly between these spaces. I haven't proved it, but I tell you it is. But anyway, I'll let you look at the rest of the solution. I guess we're out of time. Sorry. See you Wednesday. If you haven't looked at the help session already from the Thursday before break, you should, because we did talk about the test in there, and it was probably a healthier discussion than the one I just had today. Is that fair? What do you think, those of you who were here?
Going through the
I went through the old test. That was helpful.